So for laminar and fully developed pipe flow, we can use all of those equations we just covered. We also tend to use the energy equation. So recall the energy equation, P1 over rho g plus V1 squared over 2g plus Z1 equals P2 over rho g plus V2 squared over 2g plus Z2 plus HS plus HF. Okay, so remember that was one inlet and one entrance. Those are all those problems where we were putting our inlets and exits at free surfaces and at exits of the pipes and all that. Same kind of thing here. We're still going to do networks with pumps and all that kind of thing in here as well. So HF, now we're going to actually define HF. HF is going to turn out to be FLV squared over 2DG. Okay, and if it happens to be laminar and fully developed, we can come up with an equation. If laminar, and fully developed, we can have an equation for F, an exact equation from our Navier-Stokes. F is equal to, I shouldn't say approximately, but F is equal to 64 over the Reynolds number. Okay. So we will use this set of equations right here all the time. Plus, if it's laminar, we can go back and use those other equations we just did. If it's turbulent, we can still use this whole energy equation and equation for HF. It's just we're going to have a different F for that case. Okay, so first, before we start doing an example, let's go back and talk about that entrance length. So we've been talking about fully developed pipe flow, but we also need to deal with entrance length sometimes. Mainly, a lot of times the problems will just be, okay, is this fully developed case? And if the entrance length turns out to be small compared to the length of the pipe, then we can say, yeah, it is fully developed, and then we can use our equations that we've already developed. So in order to figure out entrance length, well, it's just too complicated to do Navier-Stokes on. So what we're going to do is go to our Chapter 5 stuff, our experimental. And if you remember what we did, first we came up with what all properties are important to the problem. So entrance length probably, viscosity and density is probably important, diameter, velocity. Those are going to be your important parameters. Okay, so you go through your whole process, that Ipsen method, to get your pi groups, and you end up with entrance length over d equals a function of rho VD, surprise, over mu, it's Reynolds number. Okay, and so then if we do experiments, we're going to get our Reynolds number is about, or entrance length over d is about equal to 0.06 times Reynolds number. And I say about because this is from experiments. If it's laminar, we'll get something different if it's turbulent. LE over D is approximately equal to 4.4 times Reynolds number to the 1/6 power. Okay, so for example, if we have flow in a one inch pipe with a Reynolds number of 2300, let's find the flow if it's laminar or if it's turbulent. It could be either at 2300 because remember that's the critical Reynolds number. So if it's laminar, LE over D equals 0.06 times the 2300. That comes out to 138. So therefore our entrance length equals 138 times our diameter, which is 11.5 feet. If it's turbulent, our entrance length, remember that's the area before the boundary layers meet, before it becomes fully developed. It's 4.4 times 2300 to the 1/6 power. It's to the 1/6 power, which equals 16. So our entrance length is 16D, which equals 1.3 feet. All right, so therefore the laminar boundary layers grow much faster than the turbulent boundary layers. And let's go ahead and do an example. Here we have flow in a horizontal pipe. Okay, first of all, is it laminar or is it turbulent? Okay, well, again, Reynolds number determines that, so let's calculate the Reynolds number. And Reynolds number, if you remember, our VD over nu. We need a V because we've got a Q. We don't have a V, so we better calculate it. Q over A. And remember, this V in Reynolds number is your average velocity. Okay, it's not the maximum velocity or anything else. So we have a Q, 0.00848 meters cubed per second, and our area is just pi r squared, 0.03 meters squared. We get 3 meters per second. Okay, so Reynolds number, 3 meters per second, 0.06 meters, over 0.0002 meters squared per second. Turns out to be 900, and that is less than 2300, so laminar. Of course, laminar is what we're studying. All right, part B, find the pressure drop per meter. Find delta P per length. Okay, and that would give you pressure drop per meter, right? Or find delta P if length equals 1 meter. Either way works. Okay, so here we have our pipe, and again, remember on these energy equation problems, which all these are going to be, label your inlets and your exits. Okay, let's also put in here a coordinate system, x, r, theta. Okay, so since it's laminar, we're going to actually have two methods for this that we could use. Most of the time what we do is use the energy equation. And we do that for laminar or turbulent, and energy equation's nice and easy, so usually that's where we're going to turn. Okay, but we have the other option since it is laminar, and that's just to use that laminar flow solution that we had. Because it has that dP dx in it, and we can use that because dP dx is a constant, and that is going to equal minus delta P over L. And the minus is because the pressure is dropping. Okay, so the pressure is higher here than it is there. So our dP dx would be negative delta P. So let's start with the energy equation method. So if you remember, P1 over rho g plus V1 squared over 2g plus Z1 equals P2 over rho g plus V2 squared over 2g plus Z2 plus HS plus HF. Okay, so once we write down our equations here, first thing you want to do is cancel out terms, as many terms as you can. Well, we got a horizontal pipe, so Z1 is going to equal Z2. Also, this pipe area isn't changing, so because of conservation of mass, that means V1 has to also be V2. So that cancels out. No pump or turbine between H1 and H2, so that cancels out. So all we're left with here is P1 minus P2 equals rho g HF. Okay, and if you remember, we had an equation for HF, rho g times FLV squared over 2dg. G's cancel. And what we want to do is just bring that L over. And we're going to get P1 minus P2 over L equals rho F V squared over 2D. All right? And that's what we're looking for. So what we need now is that F. And F for laminar flow is just 64 of the Reynolds number. We already calculated the Reynolds number. So that's going to come out to be 0.0711. And we can just plug in then. P1 minus P2 over L comes out to be 4,800 pascals per meter. Okay. That was method 1. Let's go ahead and do it using method 2 as well, just to show using our Navier-Stokes solution. Okay. So our Navier-Stokes solution was, well, we can use actually the Umax equation. Umax is 2v, which is 6 meters per second, okay? And that is U at R equals 0. And there's a number of ways to use this, but if I just use the Umax equation, which we already figured out, that's equal to minus R squared over 4 mu times ddx of P plus rho gz. Well, notice this rho gz is inside the ddx. dx of rho gz, well, we don't have any slant. It's horizontal. So that is equal to rho g dz dx, and that dz dx is 0 because it's horizontal. Alright, so our Umax, which equals 6 meters per second, just equals minus R squared over 4 mu dp dx. Okay, and now we can solve for dp dx, and voila, it equals minus 4,800 pascals per meter. Good thing. Came out to be the same. Okay, that was part B. So part C says find the maximum velocity in the pipe. Well, we already did that. Umax 2v, which equals 6 meters per second. Ta-da, easy. Because it's laminar. Part D says find the velocity at any R value. Okay, well that is definitely going back to our Navier-Stokes solution. We're not going to have that yet for turbulent. We may not even have that for turbulent. So, but for laminar, we can just use our U equals equation. And we had one in terms of Umax, so let's use that since we already have Umax. Umax times 1 minus little r squared over big R squared. So that's equal to 6 meters per second times 1 minus little r. And remember little r, that's your coordinate. That's just going to stay in. But our big R is 0.03 meters squared. So there we have it. At any R value. So we could plug in R equals 0.01 and figure out what the velocity is at any R. Part E says shear stress at the wall. We calculated that as being 8 mu V over D. And remembering that nu equals mu over rho, so mu equals rho nu, we can find tau wall equals 8 rho nu V over D. Plug that all in, you get 72 pascals. And finally, part F. Find the entrance length, LE over D, laminar flow, 0.06 Reynolds number, 0.06 times 900, 54. So our entrance length equals 54 approximately times 0.03 meters. Oops, D is 0.06 meters. Which equals 3.24 meters. All right. So depending on our length, the entrance length may or may not be important to this problem. All right, stop here and finish the quiz.